Hello everyone, I'm Keesang Song from AMD, and my colleague Vipin Varghese is joining the virtually from India right now. We both are part of the telco software engineering team in the server BU at the AMD. So I'm currently serving the DPDK governing board member on behalf of AMD as well. So we are all excited to present the very first topic for the DPDK Summit today. So our title isn't really intuitive to the most of people, but for those who ever worked on the maybe EAL common API call, it could ring a bell to you. So going to the agenda, here's pretty much what we're gonna cover today. As a core, density continues to increase, as you know. Chiplet-based core packings has become a key trend right now. So in AMD associate EPIC architecture, core complexes within the same chiplets share the last level cache, and then more, it will be the trend of a high density core count, CPU and GPU architecture. In contrast, packing these like a lot of logical cores within same LLC, last level cache, we can enhance the pipeline processing stages due to the reduced latency and improve the data locality. To leverage these benefits, we're going over some of the typical network application use cases and why is critical for different hardware silicon vendors, especially when you pack more execution and compute cores in the compute chips or compute complex die, we call it, or compute tiles, right? So from the industry, right? So, and now I'm gonna focus on explain how the DPDK libraries and examples can utilize the localized L cores. So this approach ensures a more consistent latency by minimizing basically the dispersion of the logical cores across the different chiplet complexes, and then enhances packet processing for sure by ensuring the data for subsequent pipeline stages like most of the network applications are having, right? So that likely to be reside within the last level cache chip level. So what is the difference in the performance? We're gonna pretty much like show up in the later slide. And using this like our kind of new prototype and kind of design. So there are multiple use cases. I'm gonna bring it up, but more focus on the like 3 different use cases, which is like VRAN and also the CDN and then packet core. So later on, kind of focusing on the packet core side, the Vipin will pretty much like showing how we actually approach the problem. Try to solve the problem. So that's gonna be the later part, and then also Vipin gonna talk about lastly that we're gonna talk about the RFC proposal to this solution. So and then talking about what is the current status of RFC, and then what's the upcoming stage, and then what are we gonna do in the future. So let's look at the virtual LAN, the VRAN as the first use cases, right? So in the 5G VRAN, virtualized radio access networks, the split between pretty much like central units and distribution units. CUNDU refers to the separation of the broadband processing functions, as you can imagine, between the centralized and distributed components of the radio access networks. To align the functional split options in the with this VRAN solution, as you know, inline or local side acceleration solution will be there, combining with the x86 CPU, right? So you can, people industry actually considering different options like options split 2, 7.2, and 7.3, and so on. But then it looks a bit overwhelming. So with all the details into it, I'm not gonna talk about those. But then what we're trying to say here is some are trying to move the general purpose solutions like x86 based, even RISC-V kind of platform with these places, we look carefully that what they do is they define the cells that have dedicated input thread, grab the EC3 packets coming through the fiber cable, for example. They do the IQ samples processing from there, and then they do the L1, L2 MAC processing and scheduling. At the end of the day, basically they convert the radio packet coming from the UE, which is called the uplink here. And then they convert into the normal IP packet, send out to the packet core, right? And then internet service provider at all. And then the reverse side, the same thing, but then it'll like IPsec would be done, and the GTPU tunneling would be done. IP lookup and other packet processing are gonna be done, and then finally it'll be converted into the IP sample, right, in the other side. So which will be pretty much like passed by the EC3 to the radio base station. So what they do in order to maintain the timing, so you can imagine, right? So how those like multiprocessors are going in order to ensure that the consistent latency will be the key here. So they define the cells, and then each cells have the multiple number of the end-to-end running protocol threads, and where the fixed functionality like MAC scheduling, and then layer conversion, and IPsec GPU tunneling, and those are running on. So for example, in this slide, I've given the uplink here. Similarly, they would be more basically the downlink in the reverse directions, and basically you have ingress and you have egress, and now depending on where you are, uplink and downlink and appropriate different layers and functions will be there. So most of the running on the each individual cores and so on. And if you see the bottom, it's not running to the completion model, run to completion model, but like a hybrid pipeline model, as you can see. So actually it's running here. And now the problem we are trying to see, and then we are actually trying to tell here is they are not really able to scale linearly, like you know, when they move from 1 cells to the 32 cell and the 4 cells, and we expect to, and people expect to get the performance, get the linear scaling, right? But when they move from the 4 cells and 6 cells, they are not really getting like 100%. It's like 80% of the scaling. As soon as they go to beyond like 12 cells, what we actually seeing is even lower scaling percentage, all the way up to like 32 cells. You can imagine, right? So the scaling factor was not even 50%. So this is a problem statement from the customer of being kind of working with. We do not pretty much that's the problem is like linear scaling issue, right? So when we increase the number of the cells, right? When it just grows and just deploying them on the more compute complex and compute die and compute tiles. So this is a pretty much generic problem statement. We just got now the same thing just goes with a different network application in some cases, just like this virtualized LAN. So the second use case is I'm trying to kind of show up here is a typical CDN content delivery networks workload that present the unique also challenges and opportunity for the optimization. So mostly the scaling issues in the CDN net workload can be attributed by the many different factors due to the high concurrency, because CDN handles numerous concurrent requests, which stress the CPU and memory resources, right? And then I/O intensity, and then content variety, right? So because the CDN serves the variety tie up to the content, static files and dynamic content and streaming media. Each one of them, right, with a different processing requirement. And then also the cache hierarchy complexity that comes into the picture. CDN employs a multi-level caching, like memory. You can imagine the different RAID, like the hard disk in the storage networks, right? Which adds more complexity actually to the data access patterns. And then lastly, maybe the load variability, and then geographical kind of distribution, as you can imagine. All those like CDN nodes are distributed globally, right? So this CDN scalability issue, or also people easily think that is using the simple 5-tuple like hashing algorithm actually across the multiple thread does not really scale linearly here, right? So, and then the destination IP and then content caching, which example is most likely destination IP plays a significant role in the determining where the content is cached or not. But this is fundamentally true for the most of the CDN architectures. You know, as I said in the beginning, most of the content locality and then the cache key formation that many CDNs uses destination IP as a part of the cache key, right? And then also, you know, based on routing table, they just do the routing kind of decision. Then the destination IP, and then that the content caching is not. It's basically the one that they can make the routing decision, right? So which is indirectly the affect the caching by the determining the which edge server handles the packet. So cache line and ping pong, and then memory access is another factor in the scaling issues here. So I'm not gonna go into the detail, but pretty much that problem we just trying to see is multiple threads, updating the metadata, and then also the sharing the data structures like, you know, global hit counters and frequently access to the load, and then causing this load balance information should be updated across the, in our case, it's different core dies and complex for these logical cores, right? And also it adds up by the memory access for the cache lines, right? So if cache misses happens due to the contents not being, you know, there in the local cache, then and also the large content items, right, can span multiple cache pipeline, right? That's causing the more memory fetches and thread migration, and eventually that causes the loss of the cache locality, right? So that's the problem we can see from the CDN. I like to just hear the third use case is coming. We wanna focus on this packet core networks. You know, pretty much the same example. We've been working with a customer, different customers. I mean, they are proprietary solutions, some of them, and they are not really all local-like. But we actually found there's pretty much like things that we can interesting enough to see how we can actually address the issue. And from now on, I think I'm gonna hand it over to the Vipin Varghese from the online, so he can just talk about the packet core use cases and then see how we actually resolve the problem. So I will leave it to the Vipin. Vipin, are you there?
So just to recap, the three different use cases what Keesang had shared highlights the problem statement from the customer. Now, based on our debugging and over the last 2.5 years, what we stated to realize there is a specific pattern for all the problems. Let me try to talk about a couple of things here. As long as our capacity on the NIC is like 50 gig or 100 gig and using 16 L cores from DPDK, our RSS scaling is quite enough to go and grab and do the processing, whether it is running on a bare metal, VM, VF, or inside a container, things were all good. But as soon as we hit 200 Gbps or 400 Gbps, single or multiple NIC, the RSS scaling has certain conflicts. Let's take a simple example where we have two ConnectX 6 or two Broadcom Thor 200 gig NIC card. And if let's go and enable the same inner 5-tuple RSS to be activated on it. What happens is that since RSS does not take into account the PCI number or the PCI split lanes and all, there is good chances that there are scenarios where in which the same flow is being calculated by two different NICs. Packets for the two different flow for two different port lands on the same processing L core. Thus, it creates something similar to a elephant flow kind of scenario. So to avoid that, one of the idea or suggestions that we internally were trying to ask our end customers to work on is to create a PF-VF mapping. That is, for one physical NIC of 400 Gbps, split it into 400 gig NICs kind of simulated model, wherein which the packet that is coming on VF1, VF2, VF3 can be landed on specific set of LCore tiles and all. This actually is a good idea, but it does not work for all the workloads and scenarios and all based on the customer deployment and customer use cases and all. Then the so RSS has scaling is can be done effectively up to 16 LCORs with 100 Gbps. Anything beyond like 200 or 400 with multiple NICs, RSS does not solve the problem for the customers that we have worked with. Now, to pack more general purpose execution engines or specialized execution engineering, what for various technology upliftment and all, they go with multi-chiplet architecture where the CPU, memory controller, PCI, and NUMA and IO is there. AMD has a special kind of model which we'll be seeing in the next upcoming slide. I'll be talking a little bit deep onto the same too. So why this is critical, because not all use cases or most of the actual deployment use cases, even though we split the traffic with toplets or 5-tuple inner tuple RSS, it's not a pure run to completion kind of model. There is a hybrid model where we certain part of the code is locked and there is data sharing that comes into play and all. So it does not scale linearly like what we want. Now, certain cores within the tile can boost to a higher frequency. They might be a heterogeneous kind of cache sizes that is coming in. Accelerators may be present in one set of core or tile, while the accelerator might be absent in another tile. So various factors now leads to the choosing of the right L cores and all. Maybe out of the 32 L cores that we have, maybe we are only selecting 16 L cores to do specific activity because of the close proximity of the accelerators or even the higher frequency that it can run the software thing. Now, why do we talk about it? We had looked into various couple of topologies, wherein which there's a core of cluster of cores which has unique L1 and L2 caches, but they share a common system level cache. Now you can switch on or switch off the system cache, or you can partition the IO memory domain die on it through BIOS and all. Certain other vendor implements this different slightly, where the memory and CPU cores are in one domain, while the IO is split domain. In case of AMD, we have CPU cores and the L3 within same domain, which we call as CPU domain, while the IO and DDR5 and all sits into another domain and all. So various vendors sometimes might be similar, sometimes they would be little bit of difference from each other and all. So let's take AMD EPYC SoC as a genuine thing. What you see on the left hand side here is Genoa Zen 4. Now we have 8 cores of Genoa Zen 4 cores with 32 MB L3 cache per compute tile. Like that, we have around 12 compute tiles and one IO die. So the IO die houses the DDR memory, CXL, PCI connections, and secure processor and other accelerators and all. Now in BIOS, we can go and enable every L3 to be popped up as a separate CPU NUMA domain, and the NPS NUMA per socket that we have, that is dividing the DDR5 and the PCI IO interfaces into 4 equal partitions. So out of the 12 memory controller, 3 might land into domain A, 3 might land into domain B, C, D, etc. So what we are trying to get into is, in AMD case, we have CPU domain as well as we have IO or memory domain available in case of AMD. Now we took a 2-socket AMD Genoa. We tried configuring the NUMA, that is the NPS NUMA per socket, into 3 different configuration. What we get to see is that the CPUs can be identified using hardware LOC library in layer 3, that is the last level cache, layer 2, and layer 1, which is SMT1, while the IO memory in case of NUMA 0 will be combining the complete I/O from two sockets and representing as one I/O domain with 512 CPUs. In case of NUMA 2 here, one physical socket is divided into two, and since we have two physical sockets, it gets divided into four. So six of the memory controllers on one NUMA domain with 128 CPUs available for it. Again, the number of count for the L3 cache tile 1 still remains same across. It is only the memory and IO which gets split up when you use the memory IO domain split. So with this understanding, we took and we applied it to the UPF use case, where UPF three major bottlenecks were number of RxTX queues spreads the same UE traffic to multiple CCX. There is locking or pthread mutex lock, which allows to synchronize for the hierarchical QoS scaling issue. There is also with regard to number of locks that is getting affected concurrently can go up to number of cores used for a particular NIC. For example, when the vendor started, they were using 100 gig Intel E810 card, and number of threads that was required to do zero drop 500 byte payload processing was around 42 threads. With certain code tweaks and reassigning this, now we are able to get the core count down to 32 thread, which means we can use two CCX here and two CCX can do the work. And what happens is that we enable the NIC card, we set two RX queues, we bring in the traffic using the UE IP as a source IP for N3 and for destination IP in case of DNAT N6. We take those packets and we spread it within the same CCX. So every traffic of a particular tuple will always land within the CCX. The CCX will the locking and other areas would be within the CCX, making it run faster. Some rare scenarios, we might end up getting certain same UEIP packet across the other domains and all, which we are trying to mitigate with yet another model, which is not discussed here too. So let's take a simple scenario. What if I have LLC aware code versus LLC the zero awareness? So the DPDK or VPP application would not see any CCX at all. It just reports back with SMT off. It reports back 96 core. In case of our CCX aware or LLC aware scenario, here it will say there are 12 CPU domain where each CPU domain is having 8 CPU threads running per CCX. Now, if I go and look at the RxTX count that is required, where the special firmware from the Intel vendor E810 is coming in, we can clearly see that for every one RX and TXQ, which is a pair, there is one L core required. And in case of this particular scenario, 96 L cores were readily available, remaining 128 minus 96 L core were reused and all. So in a worst case scenario, all the 128 threads can bring traffic from the same UEIP, which causes contention and bottleneck for scaling and all. Irrespective of how your LLC is divided. Now, with this notion of LLC, now I can tell how many CCX do I need and how many threads we need to have. Thus, we were able to reduce the locking across 96 concurrent L cores to all the way down to 12 L cores. And inside the CCX with the 15 worker thread, we were able to pin it and all. And we can see substantial improvement in the packets that are getting processed too. Thus, we created a RFC V1 wherein which we were doing RT get for the first L cores, RT get for all the L cores, RT get for the first or last N L cores supported with macro. The community had come back to us and suggested couple of changes. Do not just focus on LLC, why not focus on L1 and L2 and even memory and IO domain, which was very valuable. The second opinion given was try to make use of the hardware LOC library for OS compatibility across various distros and vendors like Linux, BSD, and Windows and all. Then what we ended up in this understanding and taking the feedback was we'll create a RT get next LCore extended, which will can take the different flags. Maybe the flag is for L2, maybe the flag is for L3, maybe the flag is for the memory controller and all. But depending upon the flag, the appropriate area and appropriate mapped LCore threads can be used within the DPDK application. Now, the V2 patch, which we are which we would be sharing by the end of Friday or coming Monday is RT get next LCore extended and RT get next N extended, where N can be at starting or from the end. That is a plan. So using these two APIs and using the unsigned 32 flag area, we can selectively select whether it is L1 empty thread, L3 or IO domain and all. But this would add a extra dependency of hardware LOC library. Time being, what we are thinking is that we'll use package config to identify whether hardware LOC library is present or not. If it is not present, we will go with the traditional approach. That is an older approach where all these APIs would then behave as if it is RT get next telco. That's the current plan. So let's say we have the library, we compiled it and we compiled our application and ran it. Within the RTL EL in it, just like how RT get CPU, get PCI and other devices are explored, we would go and call RT get topology, which internally would be calling the hardware LOC library and populating how many L1 CPUs L cores are available, how many L2, L3 appropriate CPU cores are available. And with that information, then whenever the end user asks, get me all the L cores, get me all the L1 SMT thread, sibling threads and all those different things we can do once the RTL init is successful. We are exploring and we are trying to make internal changes to event dev and packet distribute libraries, but because in event dev we are creating multiple queues or stages where most of the traffic are processed by the worker thread. Now this gives us a unique opportunity to pick up one RxQ or one port, one RxQ and confine that complete thing within inside the same tile, thus taking the advantage of the same L3 and L2 data sharing and all. So just to give a glimpse, if we did not have the LLC awareness in case of AMD Epic, the packet distribute library will just simply blindly put the packets across multiple L cores within the CCX. And here mostly it would be in sequential formatto. But with LLC awareness, what we are telling is these are the set of the worker cores. So get the packet, the small red boxes that you have will do the individual packet distribute within the pilots worker threads and all, thus retaining the L2, L3 and confining it within inside the same LLC and doing less work. This is what we were trying to bring in, a completely vendor agnostic, easy to use API, which can encapsulate and give us the right set of L cores for the purpose and all. With that, I thank everyone for allowing us to come and share this knowledge with you all. Thank you all.
Hey Vipin, can you hear us?
Yes, I'm here.
Hey Vipin, it's Edwin. Great to hear your voice again. Hey, can you take us quickly through slide 13 and explain what the exact benefits are? Right, I don't actually understand the comparison between no LLC
Sure.
awareness and LLC awareness.
Sure. Keesang, can you help on slide 13? Okay. So I'll just quickly repeat this part. What we did was, with that understanding of last level cache, the RFC1 that we had, we helped the customer to change how they identified the cores. Initially, what they were doing was, whether it is Ampere, Intel or AMD, they were taking all the L cores from both the sockets and they were creating a single port container. And whether it is 100 gig NIC or multiple 100 gig NICs, they were just spreading the RxQs across all the 128 L core threads. So, and in all the three platforms, they were not getting to see linear scaling. So to address this problem, what we did was, we gave them this notion of this LLC and enabling in the BIOS for AMD in case of L3 as NUMA, or in case of Ampere or Intel, the clusters were, or the tiles were formed. And with that, with this LLC information within inside that process, we were able to just spread 100 gig across each cluster tile. That was the initial starting work that we did, with which we were able to get down from 42 threads to all the way to 36 threads. Then we started looking at how the hierarchical QoS stage was working. So those were the two major changes what we did. Okay, I'll take a pause here.
Is that answer for you? Yeah. Well, any other question? Can you pass the mic on?
Keesang, please do put it on the chat too, okay? If in case I drop or not hear properly.
Okay. You cannot hear properly? Yeah,
No,
I'll
I
repeat
can
the
hear
question.
in case, yeah. Keesang, can you go to slide 12? So one point I missed out to share. I did talk about having the accelerator getting impacted also with this. Now, why we brought this in is there is a feature called as smart data cache injection on AMD EPYC SoCs. So using that feature and the PCI TLP header, we literally can push the packets to appropriate different tiles too. So even to identify which tiles to steer the traffic from any accelerator which supports TLP header, this LLC was also useful for us too. So these were the promising reasons why we went and implemented in vRAN and UPF packet core solution. Just to give a context.
Yeah, so the RSS problem that you described, where you try to RSS to a large number of cores, and I think you get imbalances, isn't that really a problem or a constraint of the RSS implementation? I mean, if you could get an even balance of RSS to a large number of cores,
or smart RSS. Yes, I agree totally. So ideally, what I would have envisioned is if we had a simple foundation NIC which supports double RSS, the first 5-tuple RSS will choose some of the L cores as a parent RX thing, and the second RSS from the metadata could be used for steering to the worker. So any smart or foundation NIC which supports this double RSS would have been the ideal thing. I fully agree to that notion. But the change in the end customer environment and all is slow. They don't also want to pick up too heavy power consuming DPUs or even FPGAs. So they are sticking with what they have. But if any NIC vendor is coming and giving them two RSS, where the first RSS on the hardware is done on the 5-tuple, and the second one, depending upon whether it is content caching or UPF, done on source IP or destination IP, or maybe inner QUIC tunnel ID, things like that, that would be very helpful. So I agree. It is a current limitation of the hardware which supports only a single RSS. I do agree to that statement.
But not only a single RSS, but just the fact that RSSing to a large number of cores creates an imbalance, right? It's more of a
yes.
Yeah, it's more of a constraint of like the size of the redirection table that's being used, right?
I agree. But like I said, we cannot force the end customer to go and pick up the latest greatest. They have their own cycle. It takes 2 to 3 years to switch over from one generation to the other generation in terms of NIC and all. So with what we have, we try to work it out. But this is not a stopgap. It has potential to where one recent work that we are doing with another customer, they were telling is that, hey, I have traffic that is coming in where it becomes a fat tunnel. So I need to select selectively tiles where I can run at turbo or boost frequency, while the remaining one are passive and all. So you can run it at P1 frequency and not the turbo frequency. So certain set of traffics which requires more processing can be sent to those tiles which are running at higher. So all those options are available with this.
Okay. Any other question? Good. Thank you, Vipin.
Thank you so much.
Keesang.
Thank you all. Thank you, Keesang.